Good morning one and all. Welcome you the first lecture on SS. Today I am going to explain the first chapter of SS, it is System Software and Machine Architecture. As we know that the system software, what is system software? What is system software? Is nothing but is a collection of programs that controls of a system. In the last class just I have discussed the difference between the system software and application software. Application software which is developed by the user, which can be run by using the system software. Yes, of course. So once we have developed some kind of program or some kind of applications, that program must undergo different kinds of phases. That program must be compiled, loaded and executed. For such kind of things, just we are using a combinations of different kinds of softwares, that is called as system software. We also can say that operating system is also one kind of system software we can say, right? So just I am going to explain what is the relationship between that system software and the machine architecture. What is machine architecture? Machine architecture is nothing but just we are going to talking about the architecture of the machine in terms of that is CPU, memory and the number of registers which are available and the data formats, instruction formats and what are the addressing modes which are available in that particular machine. So we are going to talking about such kind of things. Yes, of course, while designing the system software, whatever it might be compiler, it might be assemblers, loaders, linkers. For designing such kind of things, those machine architecture is matter. Some of the system software it is machine independent, some of the system softwares it is machine dependent. So whatever the aspects just we are going to considering here, everything it matters while designing and working of the system software like assemblers, compilers and all. So here in this session just I am going to briefing about two main architectures, how actually the assemblers and compilers will work. That is the first one is SIC machine architectures, that is the simplified instructional computer, and another one is SIC XC, just I will explain in the later session. Okay. So here whatever the machine architecture just we are taking, the main aspects of the machine architectures, these things, that is the memory, registers, data formats, instruction formats, addressing modes, instruction set and input-output instruction. Before getting to such kind of things, just I want to give a simple example. What is in this chapter we are going to using the assembly code or assembly level language code. So first we should know what is assembly level language code. First just we should know such kind of things. For example, in C programming, let me take a simple example here. In a C program, one assignment operator, one assignment statement, if I am taking some kind of assignment statement, suppose here there are two integer variables just I am taking A and B. The A it is having the value 10, B is having the value it is 5, right? So I want to assign a value with a variable with the value of B. This is the statement how we can write by using the higher level language. So while it is processing, yes of course, it will be the input. This is the source code just what we are giving. It will be the input to the compiler. What actually the compiler is going to do? It is going to translate this code from source code to assembly code. That is the assembly code. That assembly code will be the input to the assembler. Then the assembler is going to generate the object code for that instruction. What is that object code? What is the assembly level language code? First it is going to generate the assembly code for that. So the same thing we can write in the assembly level language in different way by using different kinds of instructions. As we know that, so here yes, we have taken two integers, that is the A and B. What is that A and B? It is an integer variable which holds the value 10 and 5 like this. So how actually the memory structure is there for that? In this case, for that, this is the memory structure, just we are taking the integer variable A, this is the memory variable name we can say. That is the memory variable name, just we can say the integer variable A is having the value 10 and the B it is having the value 5 in somewhere else in that memory. As we know that once we have written that program, it is having different kinds of things. instruction set as well as the data set which are required for such kind of instructions, isn't it? So while loading such kind of instructions or while loading that such kind of program in the memory, the instructions will be loaded first, and whatever the data which are required for such kind of instruction are loaded at the bottom of that memory. In this case, yes, of course, what is the main instruction is that? That is the assignment instruction. Just we are going to assigning the B value to A. So this is the instruction. So for this one, for the same code, it can be written by using the assembly level language code. Yes, of course, for such kind of things, we are using some kind of temporary variables, otherwise some kind of special purpose registers there. So in this case, the same thing, just we can write the same by using the assembly level language code. What we can do is of course integer A here in the higher level language, first we are going to defining the variables what we are using in that program, then we are going to write the instructions. But in the assembly level language, first we are going to write the instruction and then we are going to defining those variable at the bottom, at the end of that program. In this case, how we can write the same program, how we can implement the same program by using the assembly level language program. So what we need to do is we have to store whatever the value which is present in the memory location A to the memory location B. What we can do for this, first we are using the instruction set, that is load accumulator. LDA means it is load accumulator. Load accumulator, it is going to copying the data from memory to register. Accumulator is a register. It is going to copying, it is going to loading the value from the memory location to the register accumulator. So from where just we are going to loading? From the memory location A. From the memory location A. So means it is going to load whatever it is a register accumulator, whatever the value which is present in the memory variable A or memory location A, that is going to be loaded into an accumulator. So what accumulator it is having now? 10. What accumulator it is having? 10. So after that, I want to store the same value to the memory location B. B is already having some values. When I am inserting the new value, the older value will be erased. For that, we are using one more instruction. We cannot use load instruction here because there is a difference between the load instruction and store instruction. Store instruction, which is used to moving the element or moving the data from memory to register, store instruction from register to memory. So one thing just we should know, we cannot move the data from one memory location to another memory location directly. There is no memory to memory operation is there. So just we have to move the data to the register first, then we can move the same data to some other memory location. So here for that, just what we can use is, so just we have to store the accumulator value. What is the accumulator value it is having? 10. So just we are going to storing the accumulator value to which memory location? The memory location B. So this is the instruction which we need for the same thing here. This is high level language, this is assembly level language. It is depending on the assembly level language, it is also depending on the machine architecture. Here just I am taking simple machine architecture, that is SIC. Right. So after that, so for this program, what the memory variables which are required? A and B. What are the types of the memory variable? Integer. So means we have to mention the data type and the data variables what we are using in that program, isn't it? So in this assembly language, we are using the assembler directives for defining such kind of things. For specifying the what character we are using, the data type it is byte, the assembler directive it is byte. For defining the integer, we are using word. So means for the integer, we are using the assembler directives, it is word. It is a word. How many words? How many words and what is the value which is there? Word, right? So whatever the variable name just we are taking, that should be there in the label field. That should be there in the label field. So memory variable A, what the type? It is integer type, and what is the value which is there? The value is 10. Again, the memory variable B, it should be there in the label field, and what is the type? It is the type, it is word, that is the integer, it is going to identifying it is integer data type and what is the value, it is 5. So this is how actually we can write the same program or same statement what I have written in that higher level language program. So this is called as assembly code. So first it will be the input to the compiler, then the compiler is going to generate this assembly code. This assembly code is nothing but assembly level language code. So once the assembly code is being generated, for each and every instruction the assembler is going to generate an object code. Assembler is going to generate an object code for each and every instruction. After combining all those object code instruction, then it is going to forming an object file. That object file is ready to load into the memory for its execution like that. So this is the assembly code. Assembly code is nothing but is a assembly level language code. So once it's been done, so it will be the input to the assembler. The assembler is going to generate the object code for each and every instruction. Once it's been done, so then it is going to what? It is going to making an object file. Yes, of course. For as I told, when I am writing that assembly level language code, so why addressing modes are needed here. So here it is going to scanning the entire program instruction by instruction. First it is going to fetch this instruction. The program counter is pointing to the first instruction first. What actually is going to do is, just it is going to looking at what is LDA. LDA is nothing but load accumulator. It is having its own opcode. The object code it is having in its own opcode. So then it is going to searching for this A, where actually that A is there. So here that load instruction is at the memory location 1000. Let us assume the store instruction it is at the memory location 1003. Let us assume the variable A is at the memory location 2000. The variable B is at the memory location 2003. That is the memory address, just we can say. Let us assume. So means in this case for executing this instruction, yes, of course it has to fetch the value from the memory location A, where actually it is located at the memory location 2000. At the 2000, what is the value which is there? It has to fetch the value 10 from the memory location 2000. What is the memory variable name? It is A. But it is going to scanning that program line by line. Directly it cannot what jump to this instruction directly. So to get the value from this variable, from this memory location, for such kind of things, it is using different kinds of addressing modes. Direct addressing mode, indirect addressing mode, some kind of relative addressing mode, index addressing mode. So such kind of addressing modes it is using, that is program counter relative addressing mode, such kind of things it is going to be used. Addressing modes also differ from one machine architecture to another machine architecture. So this is how about the simple program, it can be written in the higher level language as well as in the assembly code level language. So as I said, whatever the program we have written by using higher level language, then it will be the input to the compiler. So then it is going to generate the assembly code. The assembly code will be processed by the assembler. Then it is going to generate object code for each and every instruction. So then it is going to making an object file. The object file is ready to load into the memory for its execution. It can be done by the loaders. So this is how about the instructions are going to be loaded into the memory and how actually it is going to be fetched. Now I'll get into that SIC machine architecture. So just I'm going to explaining the different aspects which are there in that SIC machine architectures here. So whatever the machine architectures, just we are taking the main aspects of every machine architectures, these things. So first we have to talk about the memory. In the SIC machine architecture, there is a simplified instructional computer. It is a hypothetical system, we can say. It is a limited version. It is having a least amount of memory space and least number of registers. Registers also varying from one machine to another machine, like that. So it is a number of instructions, everything is limited here. So here just we are taking the memory. Memory, it is just we can say that memory it is of 8 bits to form up bytes. Again 3 consecutive bytes, it is called word. So what is the word length then? 3 bytes. What is the word length? It is 3 bytes. 3 consecutive bytes it is word, and the number of the total space which is available here, it is 2 to the power of 15 bytes. It is approx 32,768 bytes. 32,768 bytes. So the addressing is, of course, there are two kinds of addressings are there. One is byte addressing and another one is word addressing. So here it is supporting that byte addressing here. This is supporting the byte addressing. So here, as I said, so it is being started from 1000, 1001, 1003. So here just I have written the word addressing here. So 3 consecutive bytes, it is forming a single word, isn't it? So means if it is like this, word addressing, sorry, byte addressing 1000, 1001, 1002. So if it is forming a word, the 3 consecutive bytes, it is going to forming a word, and the length it is for each location, it is of 8 bits. That is 1 byte. That is the 3 consecutive bytes. So most of the time just we are using the byte addresses here. Instruction length here, it is 3 bytes. So hence it requires a single word to store a single instruction here. So now I'll move to that registers. It is supporting registers which is supporting 5 special purpose registers. One is accumulator, the name it is accumulator, and X, this is the indexed register, and L, that is the linkage register. This is most important, that is the program counter, PC, program counter, and status word. This is also called as flag register. So your accumulator, for the accumulator, for some kind of SIC estimation architecture, we are using the numbers instead of that accumulator or register name here. So here the number of the accumulator is 0, this is 1, this is 2, again this is the number for the program counter, it is 8, for the status word it is 9. So here for what purposes we are using accumulator? To perform some kind of arithmetic operations, for such kind of things just we are using accumulator, because here it is not supporting, it is not providing any kind of general purpose registers. It is not providing any kind of special general purpose register. For everything just we need to use an accumulator, for loading, for storing, for adding, multiplying, dividing, for everything, for comparing, everything just we need to use the accumulator. The operation is going to be done between an accumulator with a word in a memory. So next one is index register, which is using for the addressing purpose. For addressing purpose. In the SIC it is supporting only 2 types of addressing mode. One is index addressing mode and another one is direct addressing mode. So the index register which is used for only that addressing purpose. The linkage register which is mainly using for what? Linkage subroutines, subroutine functions. That there are 2 main subroutine functions are there. Jump subroutine, that is J sub, and the return subroutine. Jump subroutine means to transfer the control to the subroutine. Once the subroutine is being executed, again the control, it should be back to the previous point or previous memory location. So for such kind of things, both JSUB and RSUB is going to refer the linkage registers. The linkage register, it is having the return address. The RSUB instruction is going to refer that linkage register value to return the control to the previous one. So the next one is program counter. As we know that the program counter is a special purpose register, that is a CPU register, which points to an instruction. The next instruction is to be fetched for its execution. For that just we are using the program counter. Again, the status word, it is the flag bit. So it is for setting the value of conditional code flag bit, that is the CC, that is the condition code flag bit. So when we are using the compare what instruction, for such kind of things, just we have to set the conditional code flag bit here, either less than, greater than or equal. So these are the 5 different registers which are available in SIC machine architecture. Accumulator for performing different kinds of operations, and index registers for addressing purpose, linkage registers for jump subroutine and return subroutine, which is having the return address, and the program counter, it is going to be pointed to the next instruction is to be fetched for its execution, and the status word, it is for set the conditional code flag bit value when we are using the comparison instruction. So this is all about the number of registers which are available in the SIC machine architecture. So the next one is data formats. So the data formats in SIC machine architecture, it is going to supporting only that integer. It is not going to supporting any floating point values. So integer, it is of 3 bytes length. Means 3 bytes length means 1 word. 3 bytes length, it is nothing but it is 1 word. For representing a character, we are using 1 byte. 1 byte or 8 bits, 1 byte ASCII value. 1 byte ASCII value, just we are using. For representing the negative number, we are using 2's complement method. For representing negative values, negative numbers, we are using 2's complement method. So this is all about the data formats which are available. SIC, it is not going to supporting any kind of floating point values here. So the next I will move to instruction format. Instruction format means what I have written, that is load A, store A, load A, like that. So that is called as instruction format. Yes, of course, the instruction format, it is having its own method to represent such kind of things. So in the SIC, the instruction format, it is of 3 bytes length. It is of 3 bytes or 24 bits. The instruction, it is of 3 bytes length. So this instruction format, it is divided into 3 parts. The first part, which is going to represent the opcode, which is used to represent the opcode. What is that opcode? Opcode is nothing but it is every instruction, it is having its own opcode. Every instruction, it is having its own opcode. So that is the load accumulator is the instruction, it is having 2 hexadecimal digit opcode here. For example, load accumulator, the opcode, it is 00. So 00, just we are going to representing in hexadecimal value. So just we are going to representing the hexadecimal value. For LDA is 00, right? So this 0, just we are going to representing by representing 2 hexadecimal value. For R sub, just I am taking another instruction, that is the R sub. For R sub, that opcode, it is 4C. For R sub, the opcode, it is 4C. For just the opcode, it is going to be represented in the form of hexadecimal digit. As we know that for representing each hexadecimal digit, we require half a byte, means 4 bits. So means we can say that 0010, for 12, C it is 121100. We can represent like this, we can write like this. So means for every instruction, for example, this is load accumulator with the memory location A. For example, load accumulator with the memory location A, means we are going to load the value which is present in the memory location A to an accumulator. So means the load accumulator, the opcode it is 0. Next bit which is used to say opcode, the bit length it is of 8 bits means, why it is 8 bits means every opcode, the opcode for every instruction it is of 1 byte length means 2 hexadecimal characters. For 2 hexadecimal characters it requires 1 byte. So means for opcode 8 bits are required. So the next one is index register. Index register it require 1 bit. So means we have to differentiate what kind of addressing mode of that instruction is, whether it is, as I said, the SIC it is supporting only 2 addressing mode, one is direct addressing mode and another one is index addressing mode. So if the index addressing mode, the X bit it is 0, then it is direct addressing mode. If the X bit it is 1, so then it is index addressing mode. So what are the remaining bits? What are the remaining bits? The 15 bits. This 15 bits it is an address. So means here the A which is the memory variable A which is at the memory location 1000, which is at the memory location 1000. So as of course it is also hexadecimal representation, just we are using. If the A it is at the memory location 1000 means that is the address of A. Where actually the A is there? At the memory location 1000. What is the address of A? It is 1000. It is 1000. So that is the address, the 15 bits. So why it is 15 bits? As of course for representing that 4 bits means it requires 16 bits, right? So whatever the 1 bit, the remaining 1 bit we are going to using to represent the mode of addressing mode, direct addressing mode or index addressing mode, although we can consider this bit also for addressing, right? So this is the instruction format for that SIC machine architecture. Every instruction it is of 3 bytes length. Among 3 bytes, 1 byte it is representing the opcode. The next 1 bit which is used to represent the index register value either 0 or 1, and the next 15 bits which is used to represent the address. The address is nothing but where actually the memory variable is there, right? So after that then I will move that addressing modes. In SIC machine architecture, it is supporting only 2 addressing modes here, only 2 addressing modes. One is direct addressing mode, and the second one is indexed addressing mode. It is not indirect, it is indexed addressing mode. Direct addressing mode and indexed addressing mode. What is direct addressing mode? In the direct addressing mode, the X bit it should be set to be as 0. If the X bit, the index register value it is set to be 0, so then it is in direct addressing mode. Index addressing mode, the X bit it should be set as 1. It is called as index register. That is the indexed addressing mode. So let me take some example for to elaborate this kind of addressing modes here. Yes, let me take some examples to elaborate the addressing modes. I will be taking first, it is direct addressing mode. Direct addressing mode. So just I am taking the same example, load accumulator with the memory location M. Just the memory variable you can give any name for that. You can give any name for that. So for example, so this is the instruction. The LDA is at the memory location 1000 LDA instruction it is there. So, but it is in the form of binary form. So, just I am taking the instruction directly there. The LDA instruction is there. So, what the instruction it is expecting? The memory location M. The memory location M is at the memory location 2000. It is having some values, whatever the value, it might be having some integer value 100 like that. So, whatever the value it might be. So, means in the direct addressing mode, it is going to be represented by using the instruction format. So, S of course, this instruction it is having two main fields, one is operator field and the operand field. Operator and the operand. Operator is nothing but is a mnemonic value, is the mnemonic field. This is symbolic field. This is the memory variables what we are using here. Mnemonic values and symbolic values. And this is the instruction we can say. Each instruction it is having its own opcode. The opcode for each, the LDA it is 00. The opcode for LDA it is 00, where actually the memory location M is there at the memory location 2000. So, here you can observe that in this instruction we are not using the index register, isn't it? So, we are not using the index registers mean to say it is direct addressing mode. Index registers is not there in that memory location, sorry, in that what instruction. In that statement the index register is not there, so hence it is there in the mode of direct addressing. So, means for that what we can do is, so just the first 8 bit it is opcode, it is opcode. What is the opcode for LDA? Opcode for this instruction, opcode for this instruction it is 0. So, means we are using the hexadecimal value here 00. So, the next bit it should be X value, that is the index register value. Is it in index addressing mode? No. So, means because this statement it is not having any index register value, hence we have to set the index register value as 0. So, before setting that one value, so first we have to write the address of the memory location M. What is the address of the memory location M? 2000, 4 hexadecimal digit. So, what is that? 2, 3 zeros, right? This is the thing. So, means just we have to look at the instruction whether it is in direct addressing mode or index addressing mode. Yes, of course it is in the direct addressing mode. What we have to do is just we can retain the same, otherwise we have to set the index register value as 0. So, means to get an object code for this instruction, so just by collecting all those values for each 4 hexadecimal digits value, just we have to collect then 0, 0, 2, 0, 0, 0. This is an object code for this instruction 0, 0, 2, 0, 0, 0. This is an object code for this instruction. We can get the object code, the assembler is going to calculate or identify the object code for each and every instruction in this way only. So, means the instruction length it is of 3 bytes, means the object code is also of 3 bytes only. It is also of 3 bytes. So, means 6 hexadecimal digits are there. How many bytes? 1, 2, 3 bytes are there, right. So, this is example for direct addressing mode. So, how we can implement the same for index addressing mode, indexed addressing mode. Let me take another example. Store character, STCH, it is another instruction. Store accumulator is different, store character is different. It is having a character value. Store accumulator, it is having the integer value like that. Store character to the memory location buffer. Memory location name is a buffer with the index register. So, means you can observe that in this statement we are having the memory as well as the index register value. For implementing arrays, we are using the index register because the array it is holding n number of elements. Just we are going to identifying the position of each and every array elements by using its index value only. So, for such kind of things just we are using the index register, index addressing mode. So for example, so here the buffer, it is a memory location. So the buffer is a memory location, is at the memory location 3000, is at the memory location, buffer is the memory location, is at the memory location 3000, buffer is a memory variable. So means it is the buffer, let us assume it is an array, right. Let us assume the index, it's been started from 3000, the index value implemented like this 0, 1, 2, 3, 4 like this, isn't it? So means let us assume at that time the index register value it is 4. At that time the index register value it is 4. So what this statement it is saying is store character. Store character means the accumulator it is having some character. Store character means from register to memory. From register to memory. So means store accumulator value. Suppose that accumulator it is having some character, it is S. It is having some character S. So what this instruction it is saying, what this statement it is saying is store character which is present in an accumulator to the buffer along with the index register value. Along with the index register value to calculate that effective address or target address. As we know that what is target address? Target address is nothing but both target address and the effective address both are same. The target address is nothing but it is the actual physical location of the value or the variable, isn't it? The target value, the target address is going to be calculated by using, so means where actually it has to be stored. To the memory location buffer. What is the memory location of the buffer? It is been started from 3000. Let us assume it will be ended at the memory location 3100. It will be ended at the memory location 3100. So means it's been started from 3000. The starting location is 3000, 3001, 3002, 3003 like this. So means let us assume I have to insert the variable is at the memory location 3004. At the memory location 3004. At that time what is the index register value? It is 4. To get the target address, I need to calculate the buffer address, the content of the buffer plus the address plus the content of the register. What is the buffer value? What is the address? 3000. What is the index register value? It is 4. What is the memory location? 3004 means it is going to store the accumulator value into the memory location 3004. That is the target address. How we can calculate the target address? Calculating the target address, it is different from one addressing mode to another addressing mode. So the same thing is going to be represented by using its instruction format like this. First 8 bits, it is opcode. Store characters, the opcode it is 54. 54 we are going to represent 10101, 4 it is 0100. This is the opcode for store character, right. So in this case index is, before setting that index register value, directly just I am going to write the address 3000 0 0, right. So this is the address, but this instruction, this statement, it is on the index addressing mode, isn't it? So what we have to do is, we have to set the index register value as 1 year. The index register value as 1 year. So means to get the object code, again we have to group 4 bits each like this. So means 5, 4, 8 plus 2 10, 10 plus 1 it is 11, 11 is nothing but B 0 0 0. The hexadecimal character for 11 it is B, that is 54. This is the object code for this instruction for that example, that is 54B0000. So this is how actually the object code is going to be generated for instruction. So here the SIC it is supporting only two addressing mode. One is direct addressing mode and another one is index addressing mode. When we are looking at that instruction only, we can say that in which addressing mode the instruction is, either direct or indexed. So the next one is instruction set. In that instruction set, we are going to categorize the instruction set into different forms. So for storing purpose, for performing arithmetic operations and for comparison, right, for to jump instructions, again subroutine functions, subroutine instructions. Subroutine instructions. For store instructions, as I said, load accumulator, store accumulator, load index register, store index register, load character. These are all called as store instructions. Load character, load index registers, load accumulator, store accumulator. These are called as what? The store instructions. When it comes to that arithmetic operations, we are using, for addition we are using add, for multiplication you are using mul, then for dividing just we are using div, and for subtracting we are using sub instructions like this. Again, for comparison we are using the instruction name, it is COMP. So means the comparison is going to be taking place. The comparison is going to be taking place between an accumulator and the word in a memory. So means, for example, just I want to compare an accumulator value with the memory location S. Let us assume the accumulator is having the value 10, the memory location S, it is having the value 20, isn't it? So means I am going to comparing the accumulator value, always comparison, it is going to comparing the value between the register and the memory location. We are going to comparing the value between the what accumulator and the memory location what are here, right? So in this case, by comparing these two values, what we can observe is the accumulator value, it is less than the value which is present in the variable or, isn't it? So it means after comparing this value, what actually it is going to do is, it is going to set the conditional code flag bit. The conditional code flag bit, either it is going to set less than or greater than or equal. Whether both the values are equal, otherwise accumulator value it is less than with the memory location value, otherwise the accumulator value it is greater than from the memory location value. Then it is going to set this the conditional code flag bit for these three values, less than or greater than or what equal. So whatever the value which is going to be set within that conditional code flag bit, accordingly the control is going to be transferred. The jump instruction, conditional jump instruction, conditional whatever the if statement you are using in C in a similar way. So accordingly it is going to jump. So means the jump instruction, it is J less than, JLT, jump greater than, jump equal. These three instructions which are there. Jump less than, if the conditional code flag bit it is set to be as less than, it is going to jump accordingly. If the conditional code flag bit it is greater than, it is going to jump accordingly. If it is equal, accordingly it is going to jump. That is the jump instructions. That is the conditional jump instruction. It is going to refer the conditional code flag bit. The conditional code flag bit for comparison what instruction. Next one is subroutine instruction. So there are two subroutine instructions which is there, that is J sub and R sub instruction. That is jump subroutine and return subroutine, both are going to refer the same linkage registers to transfer the control. The last one is input and output instruction. Along with this instruction, it is going to be providing a set of input and output instruction for testing the input and output device. For such kind of things, it is providing instruction name, it is test device and write device, read device. These three instructions, write device, read device. So these three instructions which are available regarding to that input output. Sometimes we want to get the data from some kind of input devices. Sometimes we need to display the same data onto the output devices. So for such kind of things, as we know that all the time the input and output devices are not ready. So we have to check whether the device is ready or not to send and receive the data. For such kind of things, we are going to use the test device. The test device, here we are going to giving the name of the device, which device, that is a keyboard or some kind of monitor and whatever it might be. So whether the device is ready or not. So means it is also using the conditional code flag bit to set the value whether the device, what the device just we are testing is ready or not. Suppose if the conditional code flag bit is set to be as less than, so then the device is ready. If it is set to be as equal, so then the device is not ready, means the device is busy to send or receive that data. So means it has to put into the infinite loop to check whether the device is ready or not. So next, write data. Once the device is ready, then we can write the data to the device, otherwise we can read the data from that device. So these three instruction set which are available for input output instructions. This is all about the SIC machine architecture. Thank you.